my computer. All right. Okay, thanks for the presentation. And thank you all for coming again. Just for the sake of the recording, my name is Theo de Campos, or Teófilo de Campos. I'm from the University of Brasilia, actually currently on a leave and working full-time at Vicon Motion Systems here in Oxford. And here, well, we just went through Frederico Guth's presentation. And we have here in the committee, Professor John Shaw Taylor from University College London and Moacir Ponti from the University of São Paulo. So yeah, thank you all for being here. And I'm gonna hand the word to John, and feel free to make any comments, ask questions, and yeah, it's up to you whether you want him to answer iteratively or yeah, just
okay.
Yeah, anyway, it's on you.
Thank you, Theo. Thank you, Frederico. So congratulations, a very interesting presentation. And I want to say that I endorse your conclusions and the way in which you presented the work. I think it was very balanced and sensible approach in terms of framing what I think are, as you say, very exciting and interesting results, but perhaps as yet there's still, a little ways to go in terms of making them entirely understood, let's say, or rigorous. I wondered, I'm going to just kick in with a few, discussion points, let's say. These are, don't treat this too much as questions. As I think, in terms of a master's project, this is certainly a great, the scope is very rich in that sense. I wanted to check whether you had done actually any experiments with the methods, or indeed, whether you wanted to mention any particular experimental findings that you either found hard to, reproduce or indeed, that you observed.
Yeah, I actually did some experiments, but I did not found them worth of including the dissertation. I did them very late in the process, and I basically found more or less the same results as Achille and Suato in their critical learning period, because what I did was I used the Fisher information just to measure the amount of information, the weights, during a simple training. So I took CFAR and then another, I think it was the problem of cats and dogs problem, and I just used the Fisher information. And what I saw was something like, let me just change here my video cam here. Okay, so, and what I saw was something like that. So, and this is the total amount of information. So I saw that the amount of information increased during training and then it decreased. And although I did not put it in an X and Y or like the information plane, most of the information is about X. X is much larger than Y. So this is at least shows that there is this moment where the information stops increasing and then it decreases. So I did that, but I didn't think that it fitted the dissertation, and I decided not to put it there.
No, that's fine. I wasn't suggesting you should have done. I was just curious to know. Yeah. And I wondered, in those experiments, I actually had a student do some similar experiments, whether you'd observed any effect similar to the ones that were displayed there, where the point at which the deficit is removed affects the level at which the information drops to in the network, or whether you had experimented with that at all.
Yeah, I didn't experiment specifically the critical learning period
Okay.
thing. So
Okay.
I can't say. Yeah.
Yeah. Okay.
But I do believe that it happens more or less at the same time, independent of the amount of information.
Yeah. No, I think those results are quite interesting, and to some extent, I found they were slightly contradicting the other question I wanted to kind of go into a little bit, which was this relation with PAC-Bayes. And so you mentioned there were links to PAC-Bayes, and you know that Achille and Soato had picked up on or pointed to. But you also mentioned that there was work possibly that could reformulate PAC at the end. Now, I wasn't sure whether those two were connected. That was in your final conclusion slide.
Yeah.
Maybe you could just speak a little bit about that.
Yeah. No, those are two different ideas. One is that they show. I think it's in chapter 8. I put the idea there that when you say that in the PAC-Bayes formulation that you have the log of 1 over the probability of the hypothesis, this log is the same as information. So this is the relationship that they do. And what I was talking about is that normally we talk in PAC-Bayes terms of you have an epsilon for the tolerance level, and you have your delta for confidence level. Yeah, but you don't need the two. You just need one. Beta is one represents they are both. So when you see in the information plane that shows the region, the possible region where these variables can reside, the beta is the relationship. If you the trade-off of epsilon and delta is shown there in beta.
Okay.
And what I said in the end is that I don't know. I think that Alexander Alemi from Google has done something about that, because I've read something like the abstract, but I was already writing and I had finished the literature, and I had to stop at one point, and I decided not to look further.
So 2 other thoughts around the PAC-Bayes link. And I realize this might be going too detailed, but I'm just curious if there was any, whether you thought about, one which is very, very related directly to this idea that, the weights need to forget the information about the data set, the particular data set. And which you emphasize, and I think is a very, very interesting part of, so they need to learn about the underlying distribution that generated the data set, but forget the detail of the data set, which is, kind of exactly this this point. Now you can, and I think this is the sort of PAC-Bayes bound that they alluded to, although it was, kind of a theoretical, in some sense, bound, because you couldn't actually evaluate it. But the idea was that you could actually create a bound in which the prior was the expected value of the weight vector under a randomly generated training set. And so, your prior is, you can't actually compute it, because you have to have a million data sets to do it. But let's say you could, there it is. And then your posterior, of course, is the actual weight vector you end up after training. And now the more you forget about the particular data set, the closer you're going to be to that prior, because you're actually going to be closer to the weight vector you would have got had you had a random data set. So in that sense, it's a directly optimizing this pack-Bayes, well, the KL divergence term of the pack-Bayes bound in terms of the. So I don't know whether that's something you want to comment on. I mean, I think that's a very interesting kind of idea, but yeah, any thoughts on that?
I think that is I agree that this is an interesting idea, and I do think that is what they intended to say. But I think one of the problems of this theory is that there is not many different voices saying, and sometimes different voices bring back, put focus on different things and help elucidate. And so I believe that it's the same thing. And one other thing that is related that I think is very interesting, I put it in the dissertation, and in the end, I was a little bit worried if it was like too difficult to understand what I was trying to explain. Is that whatever you choose as the prior. So if you are minimizing with the truth prior, you're using the channel information. But if you're just using a prior that you optimize it, this is the recent information, and then if you and you can get the fish information. It depends what you use to upper bound. So there are different kinds of information. So this is, I think, an interesting topic. That if I had started from another point, I had to learn so many things for this dissertation.
No, definitely. Yeah, I mean, that was the other link actually that I was going to bring out, and really perhaps to slightly counter your suggestion that this theory is in some sense not explained by traditional learning theory, which I take the way you presented it, and I don't want to dispute the way you presented it, but one of the ways in which pack-Bayes can be applied is to think in terms of the geometry of the Fisher information, because if you have low Fisher information, it means that you can be very much looser with the posterior distribution in that region, because there's less effect of varying that particular weight, because it's a very smooth local, flat local minimum. And so essentially you thereby again reduce the KL divergence between prior and posterior in the dimensions in which you have a very flat local. So looking for flat local minima actually does, using pack-Bayes, I wouldn't call that classical exactly.
Okay.
Theory,
I think I
still
included pack-Bayes in classical, like.
Yeah, but I
sense. Yeah. Well, I did that. And I think, but I do agree with you that pack-Bayes explains it all. So, and when I actually took a long time to realize that. I took a long time to realize what was missing in the explanations of the theory and what was missing in my understanding of what they were saying. And but I took a long time to realize what you're saying now. That pack-Bayes explains it all. And so I started to think, well, so if it explains it all, why bother? And that put me in the path of thinking, so why bother? And I realized that the narrative is an important point, because you are talking about the same things using different names and arriving from different places. And it helps. I think it helps. I see that after I started studying this field, I come to think much more in information theoretic terms, and I think it helps me understand.
No, sorry, I didn't want to imply that actually fact-based explains it all, because I don't think it does. But I think what I was trying to say is there are aspects that it can explain, and I absolutely endorse what you're saying in terms of it brings a different perspective, and it highlights I mean, for example, in your final slide, you also suggested there might be different optimization strategies that could be applied in the different phases that are highlighted through this method. I'd be curious to know if you have any more concrete thoughts on that. I mean, I'm not saying you should have, but is there anything you're thinking about there that might be?
No, actually, I started studying this part, and the problem is that I don't have the background in physics and statistical mechanics, and it's a whole new rabbit hole to go into, and I know that a lot of people in physics study the dispersion, and I think that these kind of studies may help in elucidate something, but I don't have the background.
I mean,
unfortunately.
I mean, what I'm saying is I buy it, but I'm really curious to know, because it feels like, you've got this relatively easy phase where you're learning until you reach this sort of crunch point where, the Fisher information is very narrow, meaning you're in a tight place, tight squeeze, because everything's constraining you. You're having to move in a very tight direction. So it almost becomes a logical problem at that phase, is sort of my intuition. And then you kind of break through and out the other side, and then suddenly, it all opens out.
It's totally different.
Yeah. And you can take a very kind of, so that I think stochastic gradient descent is probably very good for the first phase, very good for the last phase, but actually pretty crap at this. I don't know. I'm speculating. Anyway, I don't have any further questions. I think I've taken up more than my fair share of the time. But thank you again, Frederico, for a really interesting thesis and presentation.
Thank you.
Okay. Well, thank you very much. That was an interesting discussion. Yeah. I was pleased to hear that you don't actually believe fact-based explains it all. I thought he would be advocating for you. I mean, I'm sure you do, but yeah, okay, but yeah, that's.
Well, maybe I could just add one little point on that if you want me to. Yeah, but in those experiments I referred to where we did the kind of deficit work. The pack-based, the generalization actually recovers in some cases, but the pack-based bound doesn't. So it's kind of, it appears, I mean, pack-based, for example, if you do normal stochastic gradient descent, it doesn't always end at a very flat local minimum, and the pack-based bound would be quite poor using this, at least using this Fisher approach. Of course, there may be other ways of applying it. Whereas if you actually deliberately target a flat local minima, the pack-based bound gives really very tight bounds. I mean, really factor of 2 kind of bounds. So you can get very tight bounds using pack-based, but you need to adapt the learning method for deep learning, even for very deep networks. But anyway, that's just an aside. Sorry.
Okay, thank you. That's interesting. Okay, so I'm going to invite Moacir Ponti to. Yeah, for his reflections and comments and questions. Please.
Hi, Moacir.
Sure. Hi. Can you hear me well?
Yes.
Yeah.
Okay. Very well. Very good. So thanks again for inviting me. I'm on holidays, but I accepted this invitation before those holidays. So yeah, why not? Anyway, so. Nice to see you again, John and Theo, and also the others in this. And well, Fred, we discussed it a bit a year ago or so about your ideas for a dissertation, and I guess in the beginning you had this. Well, I apologize for the noise in the background. I cannot do anything about it. Sorry. But anyway, um, um, and you had this idea. You set your goal to trying to find this narrative in which the information theoretic approaches could be useful for in particular for deep learning. And in the end, what I can see from your dissertation is that you achieve a way of, let's say, meeting all those conclusions and the work that has been carried out in the last years, and you draw in the end some conclusions around those papers. So did you and I understand this is a master's dissertation, okay? So you don't have to have something that's completely novel. But can you tell me something like, did you find anything that you consider to be some novel thing,
Yeah.
or at least a path towards something that could be new, and then what do you what would
The sound now is frozen.
You froze for in the last sentence. So can you repeat?
Can you
yeah,
repeat
I
the
just
last sentence?
Yeah.
wanted if you guys the specific points that you think that you believe that you could contribute more to this discussion.
Yeah, I think I understand the question. If along the way I found things that were missing in the story that I was telling, and I think that there are possible paths, opportunities of research for me, and then I started, and I believe so. And in the beginning, so my objective was to build the digest, so to connect the dots of what has been done, and by doing so, many times I found gaps, and sometimes the gaps were in my understanding, or something that I didn't know, or something that I was not aware of, and sometimes I really didn't find at all, and some of it is lost because many of the steps that sometimes I was a little bit worried of being a too dense dissertation or boring, because I put all the steps, but I had to do that because sometimes I didn't know if something was trivial or not. And in a paper, they would say, this is intractable. And I would say, is it? Oh, so why? And, and I had to think a lot, and I had to develop something and I put all of that in the dissertation, so all the steps. But I think there were two other things. One is that that section that I put in the middle of the chapter 6 that I called intermezzo, which talks about what I call the pack channel. That I think, and more than that, all that idea that the way that I explain information theoretic learning, I think is more pedagogical than the way it's normally said. And okay, so I think this is new. I'm not sure if it's publishable, and I'm not, and maybe it can be something that is a start of something. This is one thing. Another thing is that I even didn't want to put it in the presentation, the slides, because I didn't want to shift focus. I really want the focus of the presentation be my main goal and what I accomplished, that the digest and connecting the dots, etc. But one thing is that Achille and Soato, they say that you can explain why the need for layers in deep neural networks with the fact that when you have several layers, the last layer will have less information than the first one. And if they have less information, they generalize better because they are more invariant to noise. And I agree with this point. But I was still thinking, another part was that, well, okay, but why can't you find the same, the fact that when you have 2 layers, you have more information in the first than the second, doesn't mean that if you had just a network with 1 layer, that 1 layer couldn't find a solution with the amount of information that you found in the first one. I'm not sure if that idea is so clear to others, but at least this is, for me, was a logic, not a mistake, but something that that I was trying to think about. And one thing that I didn't see anybody talking about is that okay, this information theoretical learning, you are not talking about hypothesis space. In a way, you are, because when you say that you have a representation that has some amount of bits, you are saying how many different encodings you can have. So so the amount of information, say, gives you a measure of the size of your hypothesis space, or of your, what I call a typical hypothesis space. And one possible explanation for the advantages of having layers is that in your last layer, you have an typical hypothesis space that is smaller. So and by the asymptotic equipartition property, all the different encodings, you have the same probability of finding. So you have a smaller space where the solutions are distributed, equally distributed, and I think that makes the problem computationally easier. I didn't want to put that in the presentation because I think this is an idea that needs to be improved. I put in the dissertation, but I still think that it needs improvement. I was a little bit worried with my lack of rigor because I'm not used to information theoretic problems, and so this is another area that I think that maybe is something publishable with
cool.
some work.
You know, I understand that. I think I just wanted to hear from you, from your perspective, like the main points that you believe that would be well, could be considered gaps that could be followed up in the future. And since that you mentioned some of them, I would like to comment on a few of those, because I believe in the sense of information theory, I guess from my perspective, and I do not, I'm not, it is not my field of research, but from what I have used and learned from, it is a great way of studying complexity of things. So complexity of the data, complexity of some task, and then allowing us to make decisions in particularly in machine learning. You can frame your problem in an information theory approach, and then you can think, you can try to make decisions regarding the complexity or how complex is the data and the space that you are working with. So I see that your intuition how this happens and the comparison between the hypothesis space, which is a search in which we search for something, and in information theory, in which we try to compress it. Or, let's say we would like to get rid of anything that's not useful, except from what makes me closer to the concept that I want to learn. So this is something that's very interesting. And then how do you see this idea of the complexity? Because in machine learning theory, for example, we have multiple works on trying to study the complexity of models in terms of their capacity, for example. And there are there are various ways of doing that, and this would relate to, so the more complex your model is, you have higher variance, and you have the idea of the bias and variance dilemma. And in this case, have you find anything that could, in a way, help us with this, and in particular with deep learning? Because the problem for me, when we tried to do something about it, the most difficult part, in my view, is this is this layer-based formulation, in which the representations that are generated, they have this hierarchical component, in which you cannot learn something that one layer serves as input to the other, in one sense. So when you are feeding the network, so the feed-forward part, the output of one layer will serve as input to the next one. However, this in general in sequential networks. But when you are doing actually the optimization process, the adaptation goes the other way around. So this is interesting that the hierarchy that you can find between the representations are actually found by in an inverse process. And I wonder if you have found anything that could help us formulating it better in a way that can allow us to better understand the role of those layers and the complexity of the model.
This point that you are bringing shows very well what I was talking about in the end, in the area that I see as opportunities. Because when everything that is said in the papers that I read is said in a more abstract way, so they are not going deep in taking one model and saying how do you translate those ideas to saying that the complexity of this model is exactly that, and show better all these steps that you're saying, but what I think is interesting is the idea that we shouldn't the difference from data and information. So what I mean by that, in this IBT, the complexity of a task, the complexities are of a task, okay, and the complexity of a task it depends on the information, on the information and the compressibility of a data set. So it's all in terms of information. And when you this reminds me a little bit of some talk in my qualification, viva, when Professor John said about worst case or not worst case, but not going in this area. When you think about, let's say, for example, an input space, if you have, for example, the input space of images of 1 KB, 1 kilobyte, you would say that there are 2 to 1 kilobyte possible inputs. But when you think about in information terms, you take into account the distribution in which the distribution that generates this image, the entropy of your input is some amount of bits that is less than 1 KB, and 1 KB is the worst case, and you have less, and the number of the typical, or the ones that you find 99.999% of the time due to the entropy of your input, and that's the same idea that I was trying to bring in to when you say about the hypothesis space, or the number of different functions that you can have, or what's the number of typical functions that you have, and so I do think that this seeing complexity as information helps you, and so I'm not sure if I answered your point, but what I want to try to say is that I think that it brings something to the discussion, but I think that the discussion must be done, is yet to be done. So we have to discuss that.
What I think is maybe missing, of course, it's just my view, is that in this framework, when you the optimization, as you said, is actually, well, as far as I understood, directly on the data itself. So in the representation of the data, let's say, and then the optimization is you minimize something around the data, the representation, subject to the mutual information between the data and the annotation when you are in a supervised learning scenario, right? So I that now that you mentioned that, like this was exactly would be my next question. That is, when you have a hypothesis space, so you are working on a space of functions, of admissible functions of a given algorithm or method you are working with. In the case of IBT, then you are not working in this space actually. So so
you are working. You're not working because you don't talk about it, and you it doesn't matter. But in a way, that was my argument in that part that I say that is a possible contribution. You are. Let me change here the camera, and I will try to explain with the paper here. Okay. Can you see?
Just to note that your paper is, well, your camera is upside down, but
yep.
It's upside down.
Yes.
Sorry. I'm so sorry. Here I can. I can change that.
Otherwise,
I can fix.
Don't worry.
I'm so sorry. So the other time I wrote it upside down.
But but that's okay. You didn't actually write. So.
And how now here? So
yes.
Better now. Okay. So sorry.
Yeah.
What I was trying to say is that you have your inputs here, and although they are part of a huge hypothesis space, just a very small part of it is typical. And if these are 1 kilobyte images, you can say that this input space is 2 to 1, and this is 2 to the entropy of your input. So, and your representation is I. So And when the number of possible mappings of the typical, not the all possible values of X, but the typical values of X and the typical values of Y is the number of these mappings is 2 to the information. Oops. So actually, it doesn't matter what is your model, but there is you are working in an like an hypothesis space in terms of possible mappings of X and Y, and these variables and this only it doesn't depend on the model. It only depends on the task. So it only depends on yeah. It doesn't matter if you are using a deep neural network or any other function. This measure is the measure of mappings. So maybe not an hypothesis space, but it's the number of mappings that you can have, and that's why I think that you can think that what you want is to find an encoding that is good for your task. So there is a number. Say the number of possible encodings that you can find, and as you are working on this typical space, even when your optimization change the weights of the data set and you go to a new configuration, you are also going to be in a mapping that is in this joint typical mapping. So
okay, then if you are you mentioned, for example, during your, well, not only in your dissertation but in your presentation, the role of the Fisher information to bound in the way in a way that is focused on the weights of the model, right? So you're actually, you said like it doesn't matter the model, but the task itself, the data itself that we're working with. However, you see a direct effect on the weights, which in some sense the weights are what compose the model, right? So the weights are the information that you have to process the data and find the actual representation. So I was wondering if there is something that can well, I was wondering if there's something that could help explain that, but maybe there isn't. It's also, well, as far as I
but I'm not sure if I understood this last point.
Sorry, can you repeat that? I just
I'm saying that I'm not sure if I understood. What I was like. Let me remind here the part of presentation. I'm not sure if you are talking about.
I'm just if you can.
Yeah, because
it's just about the complexity of the model itself. So what would be the impact of this formulation on the actual complexity of the model itself? Because if you say like it doesn't, of course, in this perspective of the relationship between X and Y, the mutual information between the input and the target that you want to achieve, regardless of the model, you have some number of mappings that you have. So the worst case and best case scenario. But then or typical, in the typical case, which is interesting. And then, so if it doesn't matter, then do you have any guarantee that any model would be able to be
to
used
find
in
it.
this sense?
Yeah, no, the theory doesn't doesn't help you there. No, the theory doesn't help you there. It just say that, and this is interesting because when it reminds me that when Shannon himself presented his theory, he explained that, oh, okay, there is an encoding. There is an encoding there. There is an and I can prove that it has these properties. But I don't show you how to find this encoding because I don't know. So in this sense, this is one serious limitation of the theory. It doesn't help you at all to find a model or give you this direction. But one thing that I think it's very, very important, and that for the extent of my knowledge, the only group that is using is Soato's group, is that idea of because even when you have a model and you don't know its complexity and you don't know how to measure it, and you don't know many things, and you can control you can control the amount of information by injecting noise. So when you inject noise, you reduce the number of possible encodings that you can find, and this is their information dropout. So they do that. It's an application of the theory. So in this sense, they are not saying, oh, they don't need to find a way to from explain their model and why its complexity is this how to calculate the complexity. You don't need that, because there is a way of saying the complexity of this model by the amount of information that is there, and the amount of information depends on the noise level. So you insert in noise until you find a point where the solutions that you are finding are out of the tolerance the tolerance error level that you want, and so you just in practice you don't need to calculate anything.
Okay, I see. I understand. Yeah. Thanks. One last comment is we were discussing with John about the stochastic gradient descent and the how interesting it really is, like to and how it helps connecting some of the dots in this sense. But then we can see that if you're lowering the Fisher information, the lower the Fisher information is, also the less information you have to really look for the perfect, the global minima that you are looking for. So is it something that is counterintuitive, or because even in regular SGD, when you are doing that, people often have tricks to not using the vanilla version of the algorithm in practice. Almost anyone does it, but they will try to find to accumulate the gradients of past iterations to help finding like the idea of using momentum or Adam-based optimization, those algorithms that use the first and the second moments of the gradient. Also, changing the size of the step. So this is it's a lot more common than using regular SGD, in which you go through the entire optimization process with the same step size you're going to change it, and
Mhm.
we are seeing more often using of this idea of cosine learning rate approach, in which you increase it and then decrease it, so on and so forth. So you can see that I can see there is this limitation in which, okay, we can use it to trying to find a different perspective of the same ideas. But then when you go to the practice, it looks to me that there are also those limitations in which, in the end, if you really want to achieve a very good model in the end, then you still have to do these tricks that are still very empirical in some sense. We don't have much theory to back up, but a lot of intuition.
But let me talk a little bit. I will take just one point that you said, and then I'll go further. For instance, one of the tricks is the cosine learning rate. You change the learning rate, and although people do that, it's a practice. Fast AI popularized the idea and so forth. And I knew that much before I knew anything about information bottleneck. But it makes all the sense when you see that there is a phase transition, and that you must have different the same way that you should have different strategies for maybe an idea is for the optimizer. You can have different strategies for the learning rate. So and one thing is that maybe you can know we can use these concepts to develop ways to knowing exactly when the phase transition happens, to know what is the perfect learning rate for training models. And this has a huge practical impact, because although you may found the same solution, if you do that in less epochs, there is a huge practical impact on the community. Okay, so this for example this shows one way of using these ideas to help develop new tricks for SGD. Yeah, I think this was one of the things that I was thinking about.
Yeah. Okay.
Yeah, and another thing.
Also,
now I remember another thing. One other thing is that that came from these ideas was there is a paper called Entropy SGD that tries to change SGD for these ideas. It's from the same student that found that implicit regularizer in the SGD, Chaudhary, the same Swatus student. And I think it's a paper with LeCun and others. And so there is opportunity in doing that, and they are doing some of those things. I'm not sure if this will lead to things that are in practice much better than the regular SGD, but I think they are interesting. Yeah.
Yeah. Okay. So yeah, I just want to wrap up saying that I really like your text. It introduces the subject and make very interesting interesting questions. Some of them are well answered, but I believe also that sometimes when you ask the right questions, it's much better, it's much more useful than to claim that you have answered them. So I like the way you put things in perspective of the wanted to achieve, and I think in terms of the objective that you have, which is to make this more this easier to understand and bridging those two areas. You have done a good job. So yeah, and I think I also took a lot of time here. So thanks for inviting me, and I'm satisfied with the.
Thank you.
Thanks, still.
Thank you very much. This was very interesting, and I think this this piece of work actually, makes us think in different ways. And I mean, like all sorts of questions can come up. Like, I think the most interesting. Yeah, I mean, personally, what I'm really like interested on right now would be like, okay, this work is very, tries to explain what we have out there. Would be nice. I mean, I know that some of people from Sawato's group and so on, they are trying to use this to propose new things, new techniques, and you just mentioned, right, the entropy-based gradient descent and so on. And yeah, so I think that's where I'm quite interested. But I think, yeah, it's obviously there was no time to contribute in that direction, but would be interesting to see like how this
and I think
out, right?
I'm not sure if you agree, but at least for me, one point that was really difficult to, one of the difficulties of this specific area is that not everybody, and I didn't have background in information theory and machine learning theory, and to go and really understand what they were saying. So my journey was quite huge.
Yeah,
and this was what I wanted to contribute. It makes the path of the new people a little bit easier, a little bit, at least.
I think that's what we try to achieve with master's thesis. But I mean, I'm not. Yeah, like I was hoping to go beyond that. I think you've gone on. Yeah, I don't know, towards that direction. But I'm quite pleased with the work. But yeah, and there are interesting things like, now that I'm in contact with a child that is growing and learning, I get really puzzled. Like I always get this question, why are the machine learning algorithms so bad, so stupid, right? What are we missing? Like we don't have an easy answer. Like why can they learn with like one sample or just a couple of samples, just something very basic, or even like learning a language, learning, basic things, learning to pick things up, or, well, except for, I don't know, learning to go to the toilet in the right time. That seems a lot more challenging than learning a different language, which is kind of... Anyway. So, and yeah, like the machine learning methods really like are nowhere near that, which is kind of disappointing. Like I think, or I know our natural or neural nets are much more complex probably than what we've got in the models, but it's very efficient, like in terms of energy consumption and
talking about this that I'm calling information bottleneck theory, because not even a consensus of how to call this field. One point is that it has spent, I think, the last years more or less in such an infancy as a field that is still addressing the most basic questions about the validity of the argument, and now there are some people that believed in those ideas, and they are moving on from these basic questions and trying to move on, for example, to transfer learning, where I believe that most gains will happen. And if we analyze all the huge impact that the community had on the world in the last years, it has to do with our ability to transfer learning, and I do believe that there will be, as the ideas that they had on SGD, I think there are some ideas there that use information and will help us better understand transfer and new techniques and things like that.
Okay. Right. Thank you. There's only 2 survivors from the crowd. There's basically Patricia and Louis and Pedro, who, well, Pedro is a former student, Patricia is a current student. Do you guys have any questions you'd like to ask before we wrap this up? Okay, silence. Right. Okay, so what we'll do, so there is an invitation for Moacir and John from Teams. We probably got, I hope you guys got it from, this might be an email. So like basically just use Teams to
Yep.
create a link. I'm going to stop recording.